we're going to start with the simplest one, the integral of a constant. So the integral of 5 dx. And remember that dx is telling us a couple of things. One is just telling us that the variable we're using is x. So notice this is 2x cubed dx, 1 over x to the 5th dx. It's just telling us that the variable that we're using is x. And it represents the tiny little infinitesimally small widths of the rectangles that we would be putting underneath this curve. Okay. So the integral of 5, that's like doing the integral of 5x to what power?
Zero.
The 0 power, right? Because x to the 0 power would just be 1, and that would be 5 times 1, or 5 dx. So we're going to note that on each of these, we have what's called an indefinite integral, meaning that there are no limits of integration. There's no lower limit, there's no upper limit. We're not evaluating and finding a number. We're just finding a function that, when evaluated at certain numbers, is the area underneath this curve. So we're going to use that power rule in reverse, which tells us to take the power on your x and raise it up by 1. So that's going to make this 5x to the first power. And then it says divide by your new power. New power is 1, so we'll divide by 1. And we're always going to add to the end of any indefinite integral, only the ones without limits, a constant. Okay. And I'll explain why we're adding that constant in just a second. But how can we simplify 5x to the first over 1? That ought to just be 5x plus our constant. And that's going to be our answer. That function, or that group of functions that we could write based on any constant, is an antiderivative of 5. And it represents the area underneath the function y equals 5 on any interval that we want to find. So the reason we have the plus c there is because if we take the derivative of the antiderivative, we should come back to our original function of 5. And we know that we'll get that if we do 5x's derivative, we get 5. And we can take the derivative of any constant here, right? It could be plus 1,000. We take the derivative and it's still, we just get a 5 over here. It could be minus 72. 5x minus 72's derivative is still 5. So we are looking for, in an indefinite integral, every function that when you take its derivative gives you 5. And that's 5x plus any constant. Does that make sense to everybody?
Yeah.
Cool. In a little bit, we'll put limits on here, upper and lower limits, and we'll have a definite integral, and we'll work with that. But for right now, we won't be doing that. So let's take a look at the next one, 2x cubed dx. So once again, this is just a coefficient and x to a power. So we can just use that power rule. It should become 2x to the what power? Fourth, and we'll just divide by 4 plus our constant, or we could simplify that to x to the 4th over 2 plus a constant. Good or no?
Good.
All right, what about 1 over x to the 5th? That's the same as integrating x to the what power? Negative 5 dx. And just because it's a negative exponent doesn't change how we use the power rule. It didn't change how we used it for derivatives. It's not going to change how we use it for integrals either. So integrating x to the negative 5 means we go up to x to the negative 4 and then divide by negative 4 and add our constant. And if we wanted to rewrite this as negative 1 over 4x to the 4th plus a constant, we could do that. Either one of those is perfectly acceptable. Any issues with that, or everybody okay with that?
Makes sense.
Wonderful. All right, what about the 4th root of x cubed dx? Well, that's just, again, x to a power. It's x to what power? The
34th.
3/4 power. So x to the 3/4 dx should become x to the 3/4 plus 1, or 7/4 divided by 7/4 plus a constant. And we don't really want to leave it as divided by the fraction, so we'll write this as 4/7 x to the 7/4 plus a constant. If we divide by 7/4, that's the same as multiplying by 4/7, right? Good or no?
Good.
All right, let's do some more. First one we got up here is some trig functions. So if you just look at your sheet that I sent you the link to, do you see a specific rule that is the integral of tangent over secant?
I do not.
Yeah, probably not. So oftentimes when you get trig functions, you need to do a little bit of work to simplify them. One thing you might want to do is try to turn them all into sines and cosines and see if stuff cancels out. So tangent is sine over cosine, and secant is 1 over cosine dx. And what cancels out?
Cosine.
Cosine, so we just end up with an integral of sine x dx. And that one should be on your paper. What's the integral of sine of x?
Cosine?
Almost.
Negative cosine?
Negative cosine. Plus our constant. And remember, the derivative of sine is cosine, right? So the integral of cosine would be sine, but the derivative of cosine is negative sine. So the integral of sine has to be negative cosine. Everybody good with that? And you'll get used to that. You'll just memorize that rule and know it. But everybody good there? Yeah.
On the paper, it says like sine equals just like regular cosine, not positive, like on the sheet. Or am I looking at it wrong?
I think you might be looking at the derivative rule.
Okay. Yeah. I'll take a look.
Let me open and make sure I didn't do something horribly wrong there, but yeah, you're looking at, I think you're looking at the derivative rule.
Oh, okay. Sorry about that.
No, that's fine. All right, everybody good? Yeah, so that sheet's got the derivatives and the integral rules. So just make sure you're taking a look at the right one, everybody. All right, what about this next one? 5x cubed. What does that become? Five x to the 4 divided by 4. And then the integral of cosine should be
Sine.
so plus sine x plus a constant. Don't forget the constant. If you forget the constant on a quiz, you're going to lose points for it. And you don't want to lose points for missing a constant. Same thing if you do it on the AP test. All right, what about this next one? 8t cubed, what does that become? That ought to become 8t to the 4th over 4. And note that our variables are t. We have a dt here now. And what about this one? This is 6t to the 1/2. So what does that become? It becomes minus 6t to the 3/2 divided by 3/2. And what's this one? This one is a t to the -3. So what does that become? Plus t to the -2 over -2 plus what?
C.
Plus our constant. Yep. And what do we get when we simplify? We get 2t to the 4th. This one becomes what? Minus 4t to the 3/2 if we multiplied by 2/3 to the 6th. And then this one becomes minus 1/2 t squared. And our plus of c stays as a plus of c. How are we feeling about this? Okay or no?
Yeah, that makes sense.
Perfect. All right, we'll do a couple more together, then I'm going to have you guys do a few on your own. So how about this one? X squared minus 1 squared over x squared. Bad news is there's no quotient rule for integrals. So how am I going to find a way to integrate this?
Could you maybe try first of all simplifying out the numerator and then see if there's stuff that can cancel after?
Sure. So x squared minus 1 squared, that would be x to the 4th minus 2x squared plus 1 over x squared dx. Okay, so we've expanded it out. Now what? How can we simplify it?
Could you do some form of substitution?
No. There is a method with integration where you use a substitution, and we will do that. Not today, but we'll do that tomorrow. But we should be able to do this without making any sort of substitution. We should be able to simplify that fraction down.
We separate it into 3.
Yeah, we can just separate it into 3 different fractions. Right? X to the 4th is being divided by x squared. So is negative 2x squared, and so is 1. So just write them each as if they were divided by that x squared. X to the 4th divided by x squared is x squared. Negative 2x squared divided by x squared is negative 2. And 1 divided by x squared is x to the negative 2. And now it's a nice power rule problem giving us x cubed over 3 minus 2x. And then this goes up to negative 1, and then we divide by negative 1, so minus x to the negative 1. Or if you want to write it as minus 1 over x, that's good too. So oftentimes, if you see a rational function, when the denominator is just a single term, you're going to want to expand out your numerator and just divide. So just something to note and think about as you're working through problems in the next couple of days. What about the next one?
Try and simplify the denominator.
Okay. What could I rewrite it as?
Secant of u and tangent of u.
We could, yeah. The integral of this 1 over cosine is just secant. And 1 over cotangent is just tangent. How did that help us out?
Oh, I guess it didn't do much.
No, it did. No, it helped us out immensely. We're one step from being done. Don't you recognize secant tangent as the derivative of something? What?
Derivative of secant?
Yeah, it's the derivative of secant. So the integral of it ought to just be secant. And that is one of the integrals that's on your sheet. And the integral of secant times tangent is just secant. So another one you want to make sure you have memorized. Good or no? Okay. All right, here are 4 more. I want you guys to see if you can work through these ones on your own. I'll give you 2 or 3 minutes to try and work through them. Some of them you'll need to look at some of the formulas on your paper for, most likely. So take about 3 minutes and let's see if you can do these. Ready, go. So for the first one, negative x to the negative 2, that ought to go up to be x to the -1, and we're going to divide by the -1. So that ought to just give us the negatives cancel. The over 1 is insignificant. We'll just drop that into the denominator, 1 over x plus a constant. Everybody good there?
Yeah.
All right. What about the next one? 3x to the 4th ought to become 3/5 x to the 5th. And the -2 x to the -3, that'll go up to x to the -2. And we'll divide by the -2, which will cancel out the -2. So we'll just have plus x to the -2. And then secant squared is a rule on your sheet. What is that one?
Tangent.
Tangent x plus our constant. Good. Now what about du over u squared plus 1? That's just a rule off your sheet also, right? What does that one come out to be?
Arctangent?
Yep, arctangent or inverse tangent of u plus our constant. And then down here at the last one, what's the integral of 2e to the x? That ought to just be what? If the derivative of e to the x is e to the x, then the integral of e to the x ought to be e to the x, shouldn't it? The constant in front's not going to affect anything, so the integral of 2e to the x is just 2e to the x. Everybody okay with that?
Yeah.
Okay, what about plus secant x tangent x? We've seen that one today. That one's just a secant x. And this minus root x, well, that's minus x to the 1/2. So that ought to become minus x to the 3/2. And when we divide by 3/2, that's the same as multiplying by 2/3. Everybody good there?
Could you explain again how the integral of 2e to the x is just 2e to the x?
Sure. Well, a couple things. One, just on your sheet, you should see that the integral of e to the x dx is e to the x plus a constant, right? Which should hopefully make sense because remember, derivatives and antiderivatives are inverse operations, and we know the derivative of e to the x is e to the x, so the integral of e to the x should be e to the x. And a constant doesn't affect anything, right? The constant just sits there. So if I have 2e to the x's, the derivative of that is 2e to the x's, and the integral of that is 2e to the x's. It doesn't, the constant doesn't affect it in any way. Does that help or no?
Yeah, that makes sense. Thank you.
Yep, no problem. All right, I know we're just a little over time here, but I'd really like to do these last two. So hopefully you're all cool with staying like another 2 or 3 minutes. That way you'll be able to actually like do your homework. So let's look at a couple of definite integrals real quick. We want to evaluate the integral from -1 to 3 of x cubed plus 1 using an antiderivative. So we need to take this antiderivative, and as soon as we attach limits to it for a definite integral, we no longer have to worry about the constant. And I can show you why in a second. But our first step will just be to integrate this, x to the 4th over 4 plus what? Plus x, right? And we'll evaluate from -1 to 3. And that's the notation for evaluating it from -1 to 3. Remember, the second part of the fundamental theorem of calculus said, find the function that is the integral of this, evaluate it at the upper limit, evaluate it at the lower limit, and find the difference between them. So this just becomes 3 to the 4th over 4 plus 3. That's the 3 piece, minus -1 to the 4th over 4 minus 1. And that's the -1 piece. Everybody see that? So that's our second part of the fundamental theorem of calculus from the other day, is we find the function that is the integral of this, evaluated the upper limit, evaluated the lower limit, and subtract. So what do we get? We get 81/4 plus 3 minus 1/4 minus 1. And 81/4 minus a fourth is 84ths or 20. And 3 minus -1 is a +4. So we get 24. Everybody good with that or no? Hopefully so. Now, real quickly, if we'd thrown in a plus c here, that would mean that we'd also have a plus c here and a plus c here. And we don't need those, do we? Because if I have a plus c here and a plus c here, when I subtract them, those constants are just going to go away. And that's why we don't need to put the plus c in when we're doing a definite integral. Everybody good there or no? Promise we're almost done. I know we're over, but you all good or no?
Yeah, that makes sense.
All right, we're gonna do one last one, and then I promise that'll be it. It's not that bad. We're only 5 minutes over. Sometimes we need to expand out our terms. So -1 to 1, and we'll expand this out to become r squared plus 2r plus 1 dr. And now we'll just integrate r cubed over 3 using the power rule. 2r squared over 2, or just r squared using the power rule, and plus r using the power rule, evaluated from -1 to 1 gives us a third, plus 1 minus -1/3 plus 1 minus 1, and simplify it all out. We got a third plus 1 plus 1 plus a third, plus 1 minus 1 cancels out. Looks like that's 2 2/3 or 8/3. Hopefully that all makes sense to everybody. Is that good or no? Not too bad? Perfect.